Hey guys, how's it going? Hope everybody, did okay this week. Everybody's staying healthy. Was able to get everything that they needed to get done this week through the remote learning. Hope everything was like a smooth transition for everybody. I'm kind of learning myself as we do this, but I want to thank everyone for their effort, their cooperation thus far. And what I've come up with is as you notice here, is this video that I plan to just kind of go through the PowerPoint, go through the notes that I've shared with you already inside Classroom. Watching these videos, I'm going to make an assignment. I'm going to be able to kind of track to see who opened the video and did they watch it in its entirety or not. I'll give you guys credit for doing that. So if you notice here, guys, we're in Chapter 11. And as I kind of mentioned, I think before we left, Chapter 11 is what we call chi-square tests. Some of you might be familiar with this through AP Bio classes, but we basically will look at three types of chi-square tests. All right, the first one is called a chi-square test for goodness of fit. And in this particular section here, we're going to do a lot of things that we've already kind of done. We're going to state our null and our alternative hypotheses. We're going to come up with some sort of test statistic, which in this case will be called a chi-squared statistic. We got to check to see if conditions are satisfied, and ultimately we'll get a p-value, and then we'll be able to say whether we have or don't have convincing evidence to prove our hypothesis correct or incorrect. So a lot of stuff that we've been doing the last few chapters kind of carries over here. It's just a different way of looking at it. All right. If you notice here in your notes, it says the chi-squared goodness of fit allows us to determine whether a hypothesized distribution seems valid. All right. The other two types of tests would be called chi-square tests for homogeneity, which is pretty much when we have two or more variables or two or more populations or treatments being used. And then finally, something that we might be familiar with is something called the chi-square test for independence. It allows us to see if we have convincing evidence about an association between variables. And we'll look at some examples that we looked at chapters ago. Specifically, maybe if you remember the one about like finger length and gender. So that might come back up here in the next section. All right. I think I'm mostly going to be just speaking to the PowerPoint slides. I just brought the notes up just to kind of show you where we were. But the first idea here is coming up with, how do we generate this idea of a chi-squared statistic? Well, it's basically the difference between the observed values and the expected values. And we can see if we have if our data is significant enough to say that there really was a difference between what actually occurred and what was expected to have occurred. Now, a common lesson here in teaching this is through a bag of M&Ms. All right, and if you notice in the PowerPoint slide here, they call it the Candyman, and this song came to my head that I'll play for you. Hopefully you can hear it. You've come to the right man because I'm the Candy Man. Who can take the sunrise, sprinkle it with dew, cover it with chocolate and a miracle or two. The Candy Man. So the reason why that song is in my head is because my daughter, like I've probably shared with you, loves the movie Madagascar. And I know a lot of you, we've talked about this movie, Class 1 and the penguins. And I know some of you in Class 4 also participated in the penguin costume. So anyway, so just try to bring some light to the situation here. But as you notice, so Mars Inc., which owns M&Ms, they say that they distribute their candies in a certain way. 13% for brown and red, 14% yellow, 16% green, 20% orange, and 24% blue. So should you open up a bag of M&Ms, the majority of those candies should be blue. All right. Now, what we're going to pretend happened here was that a random sample of one bag of M&Ms that had 60, our counts for what actually occurred, our observed counts were 9, 8, 12, 15, 10, 6. Okay. So our sample proportion of blue M&Ms would be 15%. Okay, well, that might be a little suspicious to some of us, thinking, well, 15%. Well, wait, Mars claims that 24% of its bags should be blue. Something fishy going on here. Are they not giving us the amount of blue M&Ms that we deserve, or that they claim we say, or they say that we should get? So when we hypothesize, right now we're just kind of speaking to just the blue M&M, and the proportion would be 24%. That's what's said to be true. Well, we think it's something different than that. All right, so we're going to define P as the true proportion of M&Ms, of blue M&Ms, and we're going to test to see if our bag is significant enough of evidence to say that, you know what, really isn't 24%. So the way in which we would do that, we would take like a one sample z-test, and that would be proportions. But now what chi-squared goodness of fit does is we're going to be able to say, okay, our null hypothesis, and there's a little writing to this null hypothesis, it's a little lengthy, is the company's stated color distribution is correct. It is what they claim to be, okay? And our HA, the alternative, would be that it's something different than what they say, okay? It's something else. It's just not correct. Another way you could write that would be if you wanted to write it out like this, but I think the sentence would probably be the best. And if you wanted to abbreviate the HA and just simply say, is not correct, I'm fine with that. Right? And as I said a few minutes ago, we're now going to get into what we would call the observed and what we would call the expected counts. All right? We would think that if our bag of M&Ms contains 60 candies, we would expect to have 24% of them blue. So 24% of them comes out to being 14.4. Right? We would do the same with the orange, the green, the yellow, the red, and the brown. We'd say, okay, well, 20% is 60 or 16% and so on. And these numbers right here, and they're okay to have decimals, all right, we would use them as our expected counts. So it's good to kind of see this in a column form or a table form where we have our observed, we have our expected. All right. Now, how do we come up with the chi-squared statistic? All right. Well, it's this formula right here. So chi-squared is the sum of the observed minus the expected squared divided by the expected. Okay. And there is a good amount of math here, especially if you had like more categories. Right now we have 6 categories, but if we had 10 or 12 or whatever, it could be more math. But I'll show you a way, probably not today, but I'll show you in the next video how to do this all on your calculator. So this is the kind of longer way, the handwritten way, but it's good to have an understanding on how to do it. So we would have to take one color at a time, and it would be, well, how many did we observe minus what we expected squared divided by, again, what we would expect, okay? Then we'd go to orange and green and yellow and red and brown and so on. And each one of those totals we would add together, all right? Those, I guess, quotients, I should say, total to be about 10.18, all right? That number right there is our chi-squared statistic, okay? So we can treat that just like we did other test statistics. On our calculator, if we wanted to, and again, I'll show you this. I'm hopeful to get the software on my computer so you can see it on your screen. But I think it's, let me say, it's menu 558 is chi-squared CDF. So your lower bound would be your test statistic. Your upper bound could just be a big number. And then degrees of freedom is your sample size minus 1. Okay? And that would get you your p-value. So if you notice here in this slide, chi-squared distributions are different than what we've seen to this point. They're right-skewed distributions, okay? They're only positive numbers for chi-squared. Start at 0 and go out to the right, increasing. Okay, you'll notice that degrees of freedom should be used are the number of categories minus 1. Okay, so in this case, we had 6 different colors. Minus 1, our degrees of freedom would be 5. Okay. Now, the slides show you kind of a different way. It shows you that way of using the table, which we're not going to use. I'll show you how to do it on the calculator. But this is what it would look like. So here's our chi-squared statistic, and our p-value would be the shaded area, meaning the likelihood that we're beyond that. okay? Um, and in this case, depending on what we would get for our p-value, which I think was a number that's between 0.05 and 0.10, and if we're testing at a 5% significance level, all right, and we got a number that was higher than 0.05, we know that we're going to fail to reject. We don't have convincing evidence to say that Marr's color distribution is incorrect, all right? A couple more slides here, all right? The next thing is the conditions. We also have an idea about these. Random, all right, 10%. One change here in the large counts, all right? It's all expected counts need to be greater than 5, okay? All expected counts need to be greater than 5. So if we go back to our M&Ms here, where these expected counts, they're all greater than 5, the condition is satisfied, we're good to carry on our test. All right. All right, here's kind of carrying out the test in its entirety. We're going to hypothesize. We're going to find our conditions. We're going to have to find chi-squared, which again, I'll show you in the calculator, get a p-value, and then the p-value will ultimately lead to our conclusion. All right. So guys, that was my quick overview. My hope is you kind of watch this video some point over the weekend, get familiar with it, check out the slides that I'll attach in Classroom, check out the notes, and go from there. And hopefully, guys, if you have any questions, feel free to ask, okay? I hope everybody enjoys their weekend. Hope everybody's staying healthy, and miss you guys. All right, talk to you soon. Thanks.